In this video, we'll be covering section 11.1, arithmetic sequences. We have three objectives. We will start by finding the explicit formula for arithmetic sequences, and then we will find arithmetic means, and we'll finish with solving applied problems using arithmetic sequences. So let's start by just talking about what is a sequence. It's pretty basic. A sequence is simply a list of numbers in a particular order. Take any numbers you want, put them in a particular order, and that is a sequence. So as a really basic example, 3, 4, 5, 6, 7, and then the ellipsis here just indicates that this goes on forever. This is an example of a sequence. Most of our sequences are going to be infinite sequences, so you're typically going to see them end with this ellipsis ... Now, order is important here. Order distinguishes between different sequences. So if I take these same numbers and switch them up, 4, 7, 3, 5, 6, that is a different sequence. One of the things that we're most interested in is coming up with formulas for sequences. Well, this one's pretty obvious what the formula will be just because we're increasing by 1 each time. Here, these seem to just be randomly ordered, so some sequences you may not actually be able to write an explicit formula for. So we're not really going to be looking much at sequences like this. Ours are going to have nice structure to them. When you have a sequence, each individual number in the sequence is called a term of the sequence. So the 3 here would be obviously our first term, and the symbol that we usually use to denote it is a sub 1. You can use any letter you want, but the common letter to denote each individual term is the letter A. And then the subscript is simply denoting the place in the sequence. So we would write A sub 1, the first term is 3, which means the second term, A2, is 4, and so on. A3 is 5, and you can just keep going that way. So this notation is simply indicating the name of the sequence, which is the letter, and then the subscript is the place in the sequence. So you can see I've written that again here. And like I said, our goal is to come up with formulas to generate these sequences. So this would be what we call the explicit formula. What it does is it enables you to just pick any place in the sequence, plug a number in, and it tells you, what that number is. So for example, if I wanted the 50th term in the sequence, I could just plug straight into this formula. The n is 50, right? This subscript is 50, so it's 50 plus 2, which is 52, right? 52 would be the 50th term in that sequence. Now, another way to think about sequences is in terms of functions. Sequences really are just functions, but they're functions whose domain, the set of all inputs, is just the natural numbers. The numbers that you plug in are these subscripts, which are just the natural numbers. So a different way of writing the formula that generates the sequence would be to use the classic function notation, f of x equals x plus 2. That is the same thing as this sequence that you see here. So there is going to be a lot of connection between things that we've done before with these sequences. Okay, so let's just practice this notation a little bit. I have 3 different sequences here, and they're each generated by a different pattern. And I encourage you to pause the video and see if you can figure out what the pattern is for each of these 3 different sequences. And then it's asking us to find the specified term to continue the sequence. Okay, so hopefully you gave that a try. In the first one here, the pattern that hopefully you recognized is that each time to progress through this sequence, we're adding 20. We add 20 to the previous number to continue through the sequence. The last number they gave us is the 4th term in the sequence. So A sub 4 is 21. We need to go all the way up to A6, so the 5th term. The next one after this, add 20 to this would be 41, and then the 6th term, the one that's we're being asked to find, would be 61. So this is a basic example. This is actually an arithmetic example, as we will see in a minute. Okay, the second one is a bit trickier. My guess is you had a hard time finding the pattern for this, and that's because you're not simply adding a number, you're not simply multiplying by a number. These represent all of the prime numbers. And it looks like we stopped on the 6th prime. So the 6th prime is 13. So then we just need to continue this out all the way up to the 10th. So I'm just going to go ahead and write these out. All right, so the next prime after this is 17, then 19, then 23, and the 10th prime should be 29. So interestingly enough, there is no way to write an explicit formula for this, at least as far as we know right now. There's no formula that can generate the prime numbers. Okay, so then the last one, this is a famous sequence. This is called the Fibonacci sequence. And the way it is generated is you take the two previous numbers and add them together to get the next one. So 1 plus 1 gives you 2, 1 plus 2 gives you 3, 2 plus 3 gives you 5, and 3 plus 5 gives you 8. We want the next one, so the next one should be found by taking the 5 and adding the 8, which gives you 13. Okay, so just 3 more examples of sequences. The kind that we're particularly interested in, though, is this first kind, which is what we call an arithmetic sequence. So an arithmetic sequence is a sequence that is generated by adding a constant to the preceding term to get the next term. That constant that you keep adding we call the common difference. So here's an example of an arithmetic sequence. And the first term is 5, and you can see we're adding 4 each time to progress through the sequence. Add 4 to 5, you get 9, add 4 to 9 to get 13, etc. So this is what we mean for it to be an arithmetic sequence. Now we call the D in this case, the D for this one would be 4. It is the common difference because if you take any two successive terms, any two consecutive terms, and subtract them in this case, like 9 minus 5, you get 4. 13 minus 9, you get 4. 17 minus 13, you get 4. 21 minus 17, you get 4. It is a common difference between any of the two consecutive terms. Now, this is going to be the case for any arithmetic sequence. So one way to kind of write that would be if you have two consecutive terms, like if we start writing this out, A1, A2, and you keep going up, if you get to a general term, you'd have a sub n minus 1, and then the next term after it would be a sub n. So this is denoting what we call the nth term, just a general term in the middle of the sequence. If it's arithmetic, then that means the difference between these two should be a fixed number, which we're calling d. In other words, what we could write is that d is equal to a sub n minus a sub n minus 1. This expression causes some confusion for people because you see this subscript here. This is not indicating the same type of operation as this. This is just indicating the subscript. This is saying the next term or the nth term, and this is the previous term. It's all the subscript is indicating. If you take the next term and the previous term, subtract them, you should always get that common difference d. Now, if we rearrange this formula, if I add this to the other side, what we end up getting is d plus a sub n minus 1 equals a sub n. And then if you just rearrange that, it turns into this. This is what we call the recursive formula for an arithmetic sequence. This is not a formula that we use very often, but it's good for us to get used to recursive formulas because they're going to show up later on in this chapter. So I'll kind of emphasize it here at the beginning, but this is not the most useful form of an equation for an arithmetic sequence. Okay, so let's try finding the common difference. So here we have an arithmetic sequence. What we're looking for is what is being added each time to progress through the sequence. It needs to be a fixed number, the same thing each time, otherwise it's not arithmetic. And we can see that here it looks like you added 2, add 2, add 2, add 2. So this 2 is the common difference. D is 2. Okay, so then this is all we were asked to find, but just to tie back into the recursive formula. That recursive formula was a sub n equals a sub n minus 1 plus the common difference d. So for this particular sequence, its recursive formula would be written as a sub n, the next term, is found by taking the previous term, a sub n minus 1, and adding 2. So this is the recursive formula, but whenever you write a recursive formula, you also need to tell what is the starting value. So you'd have to say the first term is negative 9. If you don't tell the starting value, there's no way to generate the whole sequence. Okay, let's try the next one. Okay, so this one is, we've given 3 sequences, and we're just asked to find, is it arithmetic or not? So again, what we're looking for is, are you adding a fixed number each time as you go through the sequence? So if we look at this one, looks like the difference here is 2, difference here is 3, difference here is 4, difference here is 5. So you can see we're not adding the same number. Now, there is a pattern to it, but we're not adding a fixed number. So this is not arithmetic. And we can just stop there with that one then. So moving on to the next one, we can see that we're not adding a fixed number. We are multiplying, right? This is times 3, this is times 3, times 3, and times 3. But multiplying by the same number is not arithmetic. Arithmetic has to be addition or subtraction of the same number. So this is still not arithmetic. So this turns out to be geometric, which we'll be covering in future sections. All right, last one. So notice the numbers are going down. So I'm not really adding here, I am subtracting. So it looks like I'm taking away 3, and then minus 3, and then minus 3. So the differences are all negative 3. So this is arithmetic. The common difference is what you're adding, and we are adding a negative 3 each time. So this one is arithmetic. And again, if I wanted to write the recursive formula for this, I would say the nth term is the previous term, which is a sub n minus 1, minus 3 in this case. We're taking 3 away each time, and then we would have to say what is the initial value. The initial value is 32. So that would be the recursive formula. Didn't ask for that, but just emphasizing it again. Okay, next example says find the first 5 terms of each arithmetic sequence. So we're told it's arithmetic, we don't have to test for that. Okay, it says the first term is 7, so I'm going to just record that. A1 is 7, and common difference D is negative 3. So record this again, we got 7. The common difference is saying what we're adding each time. So A2, we're going to add negative 3 to that, so we'll end up with 4. A3, we're adding negative 3 to this, so we get 1. A4, add negative 3 to the 1, you get negative 2. A5, add negative 3 to that, and you get negative 5. Okay, and that's all that asks us to do. Each time we're just simply adding negative 3. All right, the next one, it doesn't use the words, it just uses the symbols, which I guess makes it even easier. So we're starting at negative 12. The common difference is positive, so now we're going to add 5. This one was negative, so we were subtracting, but positive here, so we're adding. So A2, add 5 to that, we have negative 7. A3, add 5 to that, you have 2. A4, we're at positive 7. A5, we are, oh, wait a second here. I think I made a mistake. Okay, I lost my minus sign. So when we added 5 to this, that should have been negative 2. Add 5 to this, that's positive 3. Add 5 here, you have 8. So again, if we were going to do the recursive formula, which it didn't ask for, but we would have a sub n equals the previous term, a sub n minus 1, plus 5, and then the first term is negative 12. Okay, so we've seen the recursive formula pop up in a lot of these examples. The recursive formula is not particularly useful in most applications because I can't immediately go to any place in the sequence. For example, let's say I wanted to go all the way down and I wanted the 50th term of that sequence. I want to know what is the 50th term, and I don't want to just keep doing the same process. I'd like to go straight to it. Well, this formula won't tell us what it is. It tells us how to get it, but what it says is the 50th term is the 49th term plus 5. But I don't know what the 49th term is. So I'd have to find that first. And to get the 49th term, I'd have to get the 48th term. To get the 48th term, I'd have to get the 47th term, and I would just be going backwards through this same process. So the recursive formula is limited, at least for us. It's not going to be very useful. Okay, so let's try to generate a better formula, what we call the explicit formula that would go straight to that point. Okay, so we know that when a sequence is arithmetic, then to progress through the sequence, you are simply adding the common difference each time. So I got A1, A2, A3. I just keep adding D to progress through this sequence. So you can see I've written that here. To get A2, it's A1 plus D. To get A3, it's the previous one plus D. But another way to think of this is, to get here, I had to add D twice. Add it twice to get A3, which is what this says. It's A1 plus the 2 D's to get to A3. To get to the fourth term, I had to add D 3 times. So we can see A4 is really the first term plus 3 D's. And then obviously it keeps working here. The fifth term is the first term plus 4 D's. Now notice there is a connection between the index and this number. It's always off by 1, right? Because we did not have to add the D to the very first term, so the number of times we're adding the common difference is going to be 1 less than the index. So if we're going to write that in general, if we're on the nth term, that means I added D 1 less time than that index, n minus 1 times. So this gives us what we call the explicit formula for the arithmetic sequence. Okay, so I've just got that rewritten here. This is going to be our main thing that we're using in this section. So here we have an arithmetic sequence. They want us to find the 13th term and the explicit formula. I would find the explicit formula first. Right? I would start with doing that. In order to get the explicit formula, we need 2 things. We need to know A1 and we need to know D. Those are the only 2 things that we actually need. So we can easily see A1 is just the first term. It's negative 3. And then D is the common difference. Well, what are we adding each time as we progress through the sequence? And you can see it's 4. We're add 4, add 4, add 4. So the common difference is 4. So that means A sub n is equal to A1, which is negative 3, just putting that in here, plus n minus 1. You leave the n in. It's just like having x in an equation. We're going to leave it in there for now, and then put in the D. So times 4 there. If we clean that up, if we distribute, we're going to end up with 4n minus 4 minus 3. I've rearranged that, which simplifies down to 4n minus 7. This is the explicit formula that generates that sequence. Notice you can test it. If I want to see if it's working, A1, if I plug it into that, 4 times 1 minus 7, I do indeed get negative 3. If I jump to the last one here, A4, 4 times 4 minus 7, that's 16 minus 7, and that does come out to 9. So I've verified that that is the correct formula. They asked for the 13th term, so plug in, we've got 4 times 13 minus 7, that's 52, take away 7, which is 45. So all the way out in the 13th place, the value of the sequence is 45. If I needed the 50th term, I just plug 50 in here. Okay, let's try something slightly different. They're asking us to find the same 2 things, explicit formula and the 18th term, but what they've given us is different. They have not given us all the terms in the sequence. They've just given us the second term and the third term. Now, one thing to notice is these are successive terms. Right? This one comes right after that, which means if I take A3 and I subtract A2, I have to get the common difference. Any 2 successive terms, consecutive terms in a sequence, are going to be, their difference is going to be the common difference if it's arithmetic. So that means 15 take away 9 has to be our common difference, D. So that comes out to 6. So the only other thing we need is we need to figure out, well, what's A1? They didn't tell us the first term. Well, let's come back to this. I know that A2 is really A1 plus the common difference. And we know what A2 is. A2 is 9. We don't know A1, but we just found D was 6. Subtract this over, you get 3 is A1. So now we have the first term, and we have the common difference. So we can plug all of that into the explicit formula, which was A sub n equals A1 plus n minus 1 times D. All right, so A1 was 3. Leave this as a variable again. D was 6, and simplify. So this is going to give us 6n minus 6 plus 3, which is 6n minus 3. It's always a good idea to double check. If I plug 2 into this, notice I get 12 minus 3, which is 9. If I plug 3 into this, I'm going to get 18 minus 3, which is 15. So it is working for each of, oops, I didn't mean to do that. That should stay as an n. It's working for each of these two given terms. So then to finish it, we want the 18th term. So a sub 18 is 6 times 18 minus 3. And 6 times 18 is 108. Take away 3, you get 105. 18th term is 105. Okay, the next one. This one is always the one that causes the most trouble. It's the most work, so obviously that's probably why it causes the most trouble. So you want to make sure you're definitely getting good notes on this one. So we're asked to find the first term and the explicit formula. All we are given is the 8th term is negative 16 and the 16th term is negative 40. Okay, so let's start off with the explicit formula again. So a sub n equals a1 plus n minus 1 times d. Now this formula applies to both of these equations. In other words, a sub 8 I know is a1 plus 8 is the n, so I can put that in here, 8 minus 1 times d. If we simplify that, a sub 8 is a1 plus 7d, but we can replace a sub 8 with what it's equal to. It's equal to negative 16, right? That was given to be negative 16. So negative 16 is a1 plus 7d. Notice this equation has two unknowns, a1 and d. If we're going to find those two quantities, we're going to need a second equation. Well, we can get our second equation from this, just doing the exact same thing that we did here. So a sub 16 is equal to a1 plus 16 take away 1 times d. Right, since they're generated by the same exact arithmetic sequence, the a1s have to be the same and the d's have to be the same in these two. Okay, simplifying it again, so this is a16 is a1 plus 15d, and we can replace a sub 16 with negative 40. Right, that was given to be equal to negative 40. All right, so now we have two equations with two unknowns. In other words, we have a system of equations. And the way they're currently set up, we can use elimination to solve this system. So I guess I'll put the negative 41 on top. Doesn't matter. So just write one on top of the other. All the variables line up nicely, so that's why elimination is going to work so well for this. So we're going to subtract down. So make sure, most of the mistakes are made when you're subtracting these. You have to be very careful with your signs here. Negative 40 minus a negative 16 means you're really adding 16 to this. So we get negative 24. The A1s cancel, and then you're going to get 8D. Then divide this over, so D is going to come out to negative 3. Negative 24 over 8 gives you the D of negative 3. Okay, well that's nice. We have D, but the problem asks for A1. Well, think back to when you're solving systems. If these are X's and Y's, we just solved for the Y, so how do you get the X? Well, you plug back into one of the two equations, and it doesn't matter which one. So I'm just going to take this and plug it in here. So negative 16 equals A1 plus 7 times negative 3. So negative 16 equals A1 minus 21. Add the 21 to the other side, and you get A1 is equal to positive 5. Okay, so we now have the first thing they asked for. Then they asked for the A sub n expression. So we have all the pieces for it. We just needed D and A1. So if we plug the A1 in here and the D in here, we can get our explicit formula. So A sub n is 5 plus n minus 1 multiplied by the common difference, which I'm going to put in parentheses so it doesn't make it look like it's a subtraction there. This is our explicit formula. Let's just clean it up. Distribute through these parentheses here, so you have negative 3n plus 3 plus 5 equals negative 3n plus 8. And again, it's a good idea to test these out. Plug 8 into this, make sure you get negative 16. Plug 16 into the n and make sure you get negative 40, which you will for this problem. Okay, the next thing that we're going to look at here is probably not going to show up in your homework, but it is an important feature of arithmetic sequences, and it will make understanding certain aspects of them, I think, quite a bit easier. So our goal is we want to graph these. We want to graph our sequence. So the idea will be that the x-axis is going to be the n, and the y-axis is going to be a sub n. So to get a better handle on what the graph will look like, it'll just be a bunch of dots, but to get a better idea of it, I'm going to replace a sub n by y, and I'm going to replace the n by x. So let me do that here. Actually, I'll do it up here. Okay, so that formula would be y equals a1 plus x minus 1 times d. So the way you want to think of this right now are x and y are the variables. You got your independent variable and your dependent variable. They're the things that are going to change. A1 is a fixed number. It does not change. D is a fixed number. So these are like, put 3 here and 5 here. They're fixed numbers. If we simplify this, y equals dx minus d plus a1. So then the thing to notice is this part right here, it's just a constant number. It's negative d plus a1. So I'm going to replace that with the letter c. Since it's just a fixed number, I'm going to replace it with c for constant. And so what you end up with is this. So what I'm getting at is algebraically, these two equations really have the same structure. They're going to have the same basic type of graph. And this should look pretty familiar to us. This looks just like y equals mx plus b. So we know that the d then needs to be our slope of our, we have a line here, and d is the slope, and the c is the y-intercept. But the important thing that I'm trying to get at is the slope part of it. The common difference of, well, first of all, an arithmetic sequence is really a linear equation. Its graph will be a line. And the common difference is the slope. So let's actually see this in practice. All right, so here I've graphed an arithmetic sequence, and we can actually come up with what its equation is. So let's actually do that. We know a1 is 1. The common difference is what are we adding? So let me actually write out the terms of this sequence. The value of the sequence would be the numbers you see on the y-axis. So it would be 2, 4, 6, 8, etc. So I said a1 is 1. I meant a1 is actually 2 then, obviously. The first term is 2 here. And then the common difference is, well, what are we adding? Well, we're adding 2 as well. So a sub n is equal to 2 plus n minus 1 times 2. If I simplify this, I have 2n, actually it's just 2n. A sub n equals 2n. And what I'm trying to get at is the graph of this, which you can see with the dots here, is the same as the graph of y equals 2x. This line has a y-intercept of 0, and its slope is up 2 over 1. Notice that the scale is not the same here, so it looks the slope looks like it's off, but it would actually just be connecting those dots. This line and this sequence really are representing the same thing. It's just that the sequence is only evaluated at the natural numbers. Now, what this does is it enables us, you could graph any sequence, and you can immediately tell from the graph of the sequence whether it's arithmetic or not. So here's a different sequence, which we're calling b sub n, and you can see these points are not collinear. So that means the sequence is not arithmetic because they have to be on a straight line. So the slope is the common difference, and then the y-intercept is just the first term minus the common difference. But this is really what we care about. The slope is the common difference. All right, let's try one more application of this. So here I've got a graph of a sequence, and again, to make sure we're clear on this, this sequence starts with 3.5. That's the first term. The next term is 3.0, then 2.5, then 2, etc., all the way down. Okay, so you can see since the points are collinear, they're on a straight line, that means it is arithmetic. And we know that the common difference is the slope of that line. So d should be delta y, the change in y, over the change in x. So if you just pick 2 points, it doesn't matter which 2 points. Let's actually not pick 2 consecutive points. Let's pick 2 that are spread out. Let's just pick these 2. So the change in the y. Well, the y of this one here, we've got 3 minus the y of this one, 1.5. And then look at their x's. We have 2, take away 5. So I kind of subtracted them in the wrong order, but it'll still work here. So change in y over change in x. So in the top, you're going to get 1.5. In the bottom, you're going to get 3. So to convert this to a nicer number, we could write the top as 15 and the bottom as, oh, and I lost a negative. That denominator was negative 3. So 15 over negative 30, just moving the decimal place over or multiplying top and bottom by 10. And now you can easily see that this is really negative 1/2 or negative 0.5. So the slope of that line is indeed what the difference is. You can see it right here. We're subtracting 0.5 each time. Okay, so using that fact, let's come up with a formula for the nth term. So a sub n, we know, is a1 plus n minus 1 times d. We know the first term is 3.5. Leave the n minus 1. Common difference is negative 0.5. And then if we clean this up, you're going to have negative 0.5n plus 0.5 plus 3.5, which is negative 0.5n plus 4. So that is the explicit formula for that sequence. You can also think of this as a line that has a negative slope of negative 0.5, and it has a y-intercept. You can see if you continued back here, continued the pattern back, the y-intercept is 4. So arithmetic sequences and linear equations are really one and the same thing. You're really studying the same concept. Okay, so then to finish this, I think we're going to look at arithmetic means. So sometimes you are given 2 terms in a sequence, but they're not right next to each other. There's missing terms in between. The terms in between are what we call arithmetic means. So if we look at this here, we've got an arithmetic sequence, and let's say that these were missing, then you would say, you're looking for 3 arithmetic means between 30 and 74. That's what these 3 numbers are, the 3 arithmetic means of 30 and 74. Okay, so let's try to find some arithmetic means. Now, I'm going to show you 2 different ways to solve this. My hope is that you're going to prefer the second way, but the first way is going to use just the same concepts we've been using on the other problems. So I'm going to make a little visual thing here. We've got 16. It says 4 arithmetic means. So that means I have 4 blanks in here. Okay, now to figure these out, what I'm going to do is I'm going to say, suppose we think of this as being A1, A2, A3, A4, A5, and then this would be A6. Now, there could be terms in front of this, so like when you see this here, you'd say, well, that's not A1, it's really A2. It doesn't really matter. It won't make a difference. We're just going to assume the last number that you have before the blanks, then that's going to be A1. So what we need to figure out is we need to figure out what the common difference is, because that's what we're adding each time to move through this. So we currently know, let's move back to red. We know A1 is 16, and we know that A6, the 6th term, is 91. So let's go back to the explicit formula. A sub n equals A1 plus n minus 1 times d. Well, we already know that A1 is 16, so I can put that in. And then I can also use this. I know A6 is A1, which is 16, plus I can put the 6 in here, which means that's really 5d, right? 6 minus 1 is really the 5 there. And then instead of having A6 here, we can replace it with 91. 91 is really 16 plus 5d. And now all we have to do is solve it for d. So subtract the 16 over, which gives you 75. Let's put that up here. And then divide by the 5. So d comes out to 15. Okay, so the d is telling you what you're adding each time. So then we can just start building up to the 91. Add 15 to this, you get 31. Add 15 again, you get 46. Add 15 again, 61. Add it again, you get 76. So these are the 4 arithmetic means: 31, 46, 61, and 76. Okay, let's look at a different way of doing that process. It's technically equivalent, but it might seem a little bit simpler. So let me make that a little bit larger for you here. Okay, so the point was that each time we're adding d. To move through this progression, we're adding d each time. So the question is, well, how many times did I add d to get here? I added it 4 times to get to this term here. So that means that we took 115 and we added d 4 times to get 83. Right? This term is just 115 plus d. Let me actually write that here. 115 plus d. This one is 115 plus 2 d's, because you added another d to get there. This one is 115 plus 3d, and then the final one is 115 plus 4d's. So we can go immediately to this equation. Right? This is going to be equivalent to the equation that we had here, here for this problem. Right? If we look at that same example, we added d 1, 2, 3, 4, 5 times. Add d 5 times to 16, and that's how we got 91. So it just gets us to that step quite a bit quicker. Okay, now we need to solve this. So subtract this over. So 4d equals, is that negative 8? Or sorry, no, that's the answer. 4d equals negative 32. Divide by the 4, d comes out to, there's our negative 8. Okay, so then we can just start filling in the blanks. So let me come back here and so I can actually write the numbers in here. All right, so we are taking 8 away each time. So we have 107, take 8 away again, 99, take it away again, 91, take away 8 one more time, and you get to your 83. So these are the 3 arithmetic means. Okay, I'm going to leave this last one as an extra example if you want to try that one on your own. So I believe that completes this set of notes. Hopefully you don't have any issues, but if you do, make sure you are emailing a teacher.